Thanks, Kevin. I'm excited to be here. I'm very new to town. I just got here in January. As Kevin kind of mentioned, I spent the last 4 years in Svalbard teaching about snow and ice, 78 degrees north, northernmost research campus in the world. So it's great to be back at a latitude where the sun actually comes above the horizon in the winter. It's been wonderful getting some sun on my face during the winter months. And I'm very excited to be in this community and get to know the people around here and the people involved in this kind of work. I'm going to talk about some work that I've done that started back during my PhD in Vancouver with Dave McClung there, as Kevin mentioned, at Rogers Pass, working on some decidedly sort of low-tech methods for measuring hardness of the snow using a thin stainless steel penetration gauge like this. And so I've changed the title a little bit from what's in the schedule to sort of, I decided I should maybe just introduce a little more about what this is and what it does and how I've sort of calibrated this, and hopefully convince you that you should all be wanting to poke the snow with a thin blade in your profiles. So the objective with a measurement like this, with inserting a thin, wide blade, is to get a sense of how well bonded the snow is. How, essentially, the bonding is related to how strong the snow is, how stress waves propagate through the snow. So we want a measurement that sort of characterizes how well bonded the snow is. A thin blade, we chose a thin blade because we want the primary resistance to penetration, as opposed to, say, pushing your fist into the snow. We want the primary resistance of penetration to be just breaking bonds and just kind of moving them a little bit out of the way, not compressing the snow. And so we came up with a procedure. I mean, I literally went down to the hardware store in Golden from Rogers Pass. I went down to Ace Hardware and bought about a $5 taping knife like this. 10 centimeter wide, 4-inch blade, so this actually isn't quite the right size that I grabbed out of my toolbox to show today, but hooked it to a digital push-pull gauge, and you just poke it into the snow about 3 to 5 centimeters, fairly quickly, not a real slow push, but just kind of a poke, and then record the maximum penetration force on the gauge in the book. And for short, I'll call this TBT sometimes, just as a shorthand for thin blade test. So why did I want to do this? Why did I not want to just stick with hand hardness in addition to other measurements we made in our profiles? And that's partly because it's standard in the snow mechanics community, research community, for decades, going back to the 50s now, to use the density of the snow as the sort of primary measurement for indexing different mechanical properties of snow. So here's a graph showing from data that I collected from about like 20 different studies that measured the tensile strength of the snow, going back to the 50s. As a function of density, density was the only common variable between all these studies to compare. And the point to take home is that if you look at sort of moderate density snow, between 2 and 250, 200 to 250 kilograms per cubic meter, you can have strength values that were pretty low, which would be something like facets or depth, or it can be relatively dense, but we know that those kinds of layers are weak. But you can have snow at the same density, say a wind slab, that's very strong. So when I collected all these data, there's like 2 orders of magnitude difference in strength at a given density. So if we know density, that's not really enough to say, in this case, how strong the snow is. So we wanted an alternative measurement for characterizing properties like strength. So I spent a lot of time poking a blade into the snow in my profiles, and then we had a cold lab up at Rogers Pass. Decidedly low tech compared to what we have here at MSU, but a cold lab nonetheless. So I spent a lot of time, I don't know if you can quite see, cutting blocks of snow out of different layers in the snowpack and then carrying them into the lab and doing a bunch of fracture and different mechanical experiments with the snow to calibrate what it means when I get a certain hardness value from the thin blade. I did about 1,000 of these experiments over the course of my PhD, and pretty much for every single one I combined it with a blade measurement. So break a block of snow or flex a block of snow or do an experiment and then characterize it with the blade gauge. So I had a one-to-one comparison between what I measured in the test and the hardness. So now I have a whole series of data for different kinds of mechanical properties indexed against this blade hardness here. I've got it labeled as B on this graph. And you often get these nice linear relationships. So that if you measure the thin blade hardness, I could tell you what the, in this case, tensile fracture toughness is, which is a property that characterizes the resistance of a material to fracture. And if you used density, again, as an index variable, you'd have scatter all over this graph. So now, over the course of a PhD doing these, 1,000 different experiments, I could tell you quantitatively what mechanical properties of the snow are for a given blade hardness here. So we can give you properties like the strength of snow, fracture toughness, fracture energy, elastic modulus or Young's modulus. Most of these experiments that I did in my PhD, we were limited to tensile properties, so we were looking at slab properties and tension primarily. With the better facilities we have at the Sub-Zero lab here at MSU now, we can start to do some shear experiments as well and correlate the blade data with shear properties.
Is elastic modulus like bending in the snow?
Yeah, how bendy is it? Yeah. So then a few ways that we've been using this blade. We can calculate, if we know a gradient in hardness to the slab, we can relate a gradient in hardness to a gradient in this elastic modulus or elasticity of the snow. And it turns out that that influences how the pattern and the depth at which stresses penetrate into the snowpack if you're standing on the surface of the snow, as opposed to assuming that the snow is homogeneous, that there's no variation through the snowpack, which is the classic assumption in calculating like a skier stability index. We can go measure a gradient in hardness through a slab down to a weak layer. If we have a weak layer, determine therefore they're a gradient in this modulus, and then calculate stresses out of that. So what that looks like is I've had some graduate students working on this kind of stuff. And here this grad student measured the hardness every 5 centimeters, and we can use a few different kind of regression models to fit the data, to represent the data, and then use those sort of regression approximations to calculate the stress that would reach that weak layer for a given load on the surface. And here's an example of the difference between that kind of stress bulb calculation for a homogeneous slab versus a slab where you have a linear increase in hardness from the top of the slab down to the weak layer. So the thick bars here, K equals 0 in this case, is the homogeneous, the classic kind of stress bulb calculation, and the filled area represents the stress for a slab with a linear hardness increase from top to bottom. And the important thing to note is that the stress penetrates deeper, or you can think about it as for a given, say, weak layer depth, you've got a linear increase in hardness, you've got higher stress at that weak layer compared to if you had a homogeneous slab. So this is linear hardness increase here, so this is the sort of a right side up increase in hardness gradient calculation. All right, so there's a little more going on this graph, but I'm going to walk you through it. So this is looking at the shear stress reaching a weak layer for a given load on the surface for a flat slope versus a 38-degree slope for different approximations for kind of a gradient of hardness from the top of the slab to the bottom of the slab. Homogeneous for alpha equals 0, linear increase for alpha equals 1. So sort of a calculation of shear stress for a given load versus this angle theta, which is a measurement of distance away from where the load is applied on the surface. So 0 degrees straight below me, 30 degrees out, 30 degrees away from me. On a flat slope, there's not much difference in these curves, so it doesn't actually matter what the profile of the slab looks like if I'm walking through the flats. I generate the same shear stress below me in whatever profile that takes. And important to point out, and this may be counterintuitive, but even on a flat slope, if I'm standing here, I'm applying shear stress out and away from me at about a 30 degree angle. The shear stress is a maximum, even in the flats. So you don't need a slope angle to apply shear stress to a weak layer. Now on a 38 degree slope, so a more common skier triggering type slope, there's a big difference if I have a homogeneous slab versus a right side up slab. The stress reaching the weak layer is much greater if I've got a gradient in hardness. So this is kind of one example, and it's easy to measure these gradients by poking a blade like this into the slab, and we're working on more refined ways of calculating stresses for different types of hardness gradients. But the point is the gradient does make an important difference. So I had another grad student working on looking at spatial variability in hardness gradients by doing a sort of standard profile, doing an extended column test, and then looking at measuring a gradient in hardness through the slab every meter for 10 meters. And then at each one of these locations, you can do one of these regression fits, calculate the stress that would reach the weak layer depending on the gradient, and see how that varies across the slope. So here's a graph that just shows a dot showing the maximum shear stress at each one of those points. So based on the gradient at this point, that's some measure of the shear stress that would reach the weak layer there at each of these 10 points along that profile. And you see that there's quite some variability. And there's several places along that transect where quite a bit higher stress reaches the weak layer for a given load at the surface. And that's just due to variability in the way that the slab has settled along just a 10-meter transect along the slope. And if we sort of repeat that procedure in different places on different days, you see a similar thing where you've got these sometimes isolated locations where you've got much higher stress predicted at the weak layer, sometimes sort of groups of points together where you predict a higher stress there. And I think the sort of important take-home point from this study is that you can get these variations in the way that the slab has settled that can also contribute to kind of sweet spots, so to speak, where triggering might be more likely on a slope. So in addition to sort of variations in thickness of the slab or properties of the weak layer, you can also have variations in the way that the slab is settled and bonded and changed its gradient and hardness from the top to the bottom of the slab that can also contribute to where these unknown sweet spots are. And then we have been working to compare and see what we can, what value we can add to tests like the extended column test using the blade gauge. Here's some measurements of ratio between the blade gauge measured. Here's at the base of the slab to the hardness of the weak layer, and the average slab hardness to the hardness of the weak layer. And again, an advantage of a thin blade like this is we can poke it into a lot of weak layers, provided they're thicker, at least as thick as the blade. And certainly for the average slab hardness divided by the weak layer, this ratio does discriminate pretty well between the ECT-P versus the ECT-N, which we kind of already knew that hardness differences across the slab and the weak layer from a hand hardness was sort of predictive. This is one of these yellow flags or red flags. But we're hoping that we can sort of quantitatively do a little more with this kind of ratio between the slab and the weak layer hardness to hopefully give a little better predictive skill to cases where we have ECT-P and where we either do or don't see adjacent avalanche activity. So, kind of wrapping up then. This is an easy measurement. It's sort of, it's intuitive. It's analogous to the hand hardness. It doesn't add a lot of time. I've been working with a manufacturer in Canada that's making a small little digital attachment to pop this kind of blade onto, so it'll easily fit into your snow study kit or your pocket. Most of the existing gauges I have are still on a ship coming over from Norway. Otherwise, I would have brought an actual working working blade to show you, but I think you get the idea. This kind of measurement is more sort of repeatable, it's more objective than the hand hardness. It's more scientifically useful. If you share profiles with me that have this kind of information in there, I can do more with that than I can with a hand hardness profile, quantitatively. And then these gradients in hardness are turning out to be quite important for predicting stress transmission down to a weak layer. And I've done some preliminary work that suggests that the gradient in hardness to the slab should influence how far a fracture propagates in the weak layer before it can fracture the slab in tension. Working on that as well. And then we've been looked at a number of storm layers that first come in pretty cohesionless, and we've kind of tracked how the cohesion of the slab translates into increases in this blade hardness right up until you get to the point where fractures first start to propagate. So we've kind of found a threshold hardness at which the slab is cohesive enough to start supporting fracture propagation. And then ongoing research. So what I've showed here, we've only so far, the equations are a little nasty for calculating these stresses, and we've only managed to solve the right side up slab case. So we're sort of working on, I think we're gonna have to use numerical solutions to solve the upside down case. That's a little more complicated, but certainly important to account for. I want to certainly collect more ECT plus thin blade test data, because I think there's probably some good value added we can bring to making predictions out of a test like that by combining it with this kind of hardness. And then, of course, there's plenty of uses for this in the cold lab, certainly doing shear experiments and looking more at hardness of weak layers in shear. And then I do want to encourage people that are interested in this kind of thing to adopt this sort of measurement. So what I would really like people to think that this is a measurement worth making, and to have people start making these measurements and start a sort of dialogue about what you see with this gauge and how we can sort of work together to get some value out of it. So that's all I have. Thank you.